Yeah, it's a real honor and a privilege to have Enrico Ramirez-Ruiz with us today. Welcome. Enrico is a world-leading expert on stellar explosions, supernovae, gamma ray bursts, also the subsequent compact objects, both through accretion hydrodynamics and their gravitational wave emission. He's an expert on binary evolution, on nucleosynthesis, and also on extreme star formation in extreme environments. Enrico received his PhD in 2003 from the University of Cambridge. After that, he became a long-term member of the Institute for Advanced Study in Princeton. And since in 2007, he obtained an assistant professorship at UC Santa Cruz, where since 2013, he is a full professor. In addition, he was a Radcliffe Fellow at Harvard University in 2014 and 15. And from 2016 till the end of last year, he was a Niels Bohr Professor in Denmark. And it's a real honor, and I'm very excited to have you here today, Enrico, as you're going to talk to us on, I hope, a very wide variety of the work that you've been active in over the past years. And your talk is titled Cosmic Alchemy in the Era of Gravitational Wave Astronomy. And as per the tradition here in Heidelberg, I would kindly like to ask everyone to unmute and give you a very warm welcome, a very warm applause.
Thank you so much for having me. Now it's wonderful to be here, at least virtually, and I hope everyone is doing well and your loved ones are healthy and safe. Let me share my screen. Wonderful, and you let me know if you don't hear me well. Yeah, so I wanted to highlight first that, of course, the work that I'm going to talk to you about is being done in collaboration, particularly with a lot of grad students and postdocs. I'm attempting to be very pedagogical, so you also, if you want to stop me at any time, please do so. So I'm going to tell you about the R process and recent advances that we have made in trying to understand the R process production, particularly in neutron star mergers. So this is my outline. I'll start with getting everyone on board about nuclear properties at the R process and what are sort of the requirements needed to produce these very heavy elements. I'll tell you what sort of inference we can draw from abundance observations in stars, which, as you know, gives us deep clues to the origin of this element. So I'll tell you a few facts on that, which I think are essential in trying to understand the origin of these elements. I'll tell you about neutron star mergers as sites of our process nucleosynthesis, and I guide you through some of the observational signatures that we work in advance of course, as you know, the detection, to sort of give you a feeling of sort of the open questions, but sort of the thinking that took place before the detection of these now very famous events, 1708-17 from LIGO. And I'll talk a little bit about the lessons that we have learned from this wonderful detection and how it's really changed our views on both neutron star mergers, but also on the origin of our process. So as you know, for astronomers, this is our periodic table. This is the abundance distribution of elements in the sun. So hopefully I'll try to give you some intuition about first the odd even variation that you see there, sort of the wiggles. Something that it's incredibly important to realize is that the abundance peak in this abundance pattern really correlates with what we call these closed neutron and proton shells. You can kind of see it very clearly here. And there's a few things that you will realize that are intimately linked to nuclear structure. The first, as you know, is that iron is the most bound element in the universe and is the heaviest element in which you have equal number of proton and neutron closed shells. You can see that. And as you go above iron, what you see is that the stability of these elements actually require a significantly larger number of neutrons than protons. You can see that, for example, when you go to lead, which is doubly magical, where Z is 82 and N is 126. So what I'm going to talk a lot about, I don't know, see you my cursor, but is basically trying to really understand the abundance peaks. And something that I'm going to highlight here is, of course, this peak and this peak, which at first sight, it appears not to correlate with nuclear structure. This is, of course, the R process. And I will basically give you an intuition as to why it does relate to nuclear structure. But the issue is that these elements are really formed far away from stability. Okay, so there's really two big impediments to making elements above iron by basically electroweak reactions or charge reactions. The first is, of course, that the Coulomb barrier drastically increased with atomic number. So, reactions that happens inside stars, do not have enough sufficient energy to actually produce such reactions. And in addition, as you know, the reactions have to be endothermic. That means that because iron is the most bound nuclei, in order to make heavier elements, you have to give energy to the system. So that impediment largely really prevents these nuclei to be formed by charge reaction, and they are primarily formed by neutral capture reactions. And we call, as you know, astronomers are not that intuitive with their names, but we call S as the slow process. What do we mean by that? That when you capture a neutron and you beta decay, if the time scale for capturing neutrons is slower than the beta decay, we call that the S process. Yeah, so that means that you're very, very close to a stability when you actually undergo the S process, because you capture a neutron, then you beta decay, and then after a certain amount of time, you capture another neutron and so forth. And you move very, very close to the beta equilibrium line. Now, for the R process, you have to capture neutrons much faster than you beta decay. So that time scale is, in fact, incredibly fast. And we'll talk a little bit about the requirements that you need to actually capture these neutrons quickly. And what I'm going to emphasize today is really try to understand how you have, this is what we call the first peak of the S process, the second peak of the S process, and the third peak. And the R process, seems to basically be shifted to the left. As you see, this is the third, second, and first peak. And I'll tell you a little bit about why that's the case. And in addition, we won't talk about the rare air peak, but this is an interesting peak that at first sight is actually not related to nuclear structure, but if you're interested, I can tell you a little bit more about the, how these elements are actually made. Okay, so of course, I'm going to spend a significant amount of time in this plot trying to give you an intuition about how these R process elements actually arise. So what I'm showing here is proton number as a function of neutron number. The first thing to highlight is where the stable nuclei live. So the stable nuclei live here in black. Yeah, this is where the stable nuclei are. Another important thing to highlight is if we capture a neutron, we move in this direction and then we beta decay. So this is how we move in this plane. An important thing is, if I'm a stable nuclei here and I move, far away from equilibrium, which means I keep the same number of neutrons but decrease my number of protons, the time scale for beta decay drastically decreases. Yeah. So as I move further and further from stability, the lifetime of these nuclei starts being incredibly short. And this is very, very important for us to highlight as you move further away from equilibrium. So this is what the colors basically highlight there. Then here I'm showing a typical R process pathway. This is with separation energies of, a few MeV. And the thing that you highlight immediately that you realize is that, these R process pathways are really captured relatively far away from equilibrium. So if you look at this R process pathway, you look at the time scales, you realize that you have tens of milliseconds in order to capture neutrons. And immediately you lead to the conclusion, which was of course done almost 100 years ago, that people realize that the only objects that have a dynamical time scales of tens of milliseconds are basically neutron stars. So either when a neutron star is born, you actually attain those timescales and densities, neutron densities, or when two neutron stars merge. So we're going to talk a lot about how to make these nuclei. Another important thing to highlight here is basically the position of these closed neutron shells, which of course are related to nuclear structure. These are the so-called magic numbers, 2, 8, 20, 28, 50, 82, and 126. And these basically, in these nuclei, are stable, and as a result, they don't really want to capture neutrons. So that's an important thing to highlight, that the neutron capture cross-section in those particular positions actually drastically decrease. To illustrate this, I'm going to show you, from a textbook, the Clayton textbook, the neutron capture cross-sections of nuclei in the S process. So this is with neutron energies of about 25 kiloelectron volts. So what are the things that you notice? The first thing that you notice is, of course, that odd mass numbers tend to have higher cross-sections than even nuclei. And if you remember, the wiggles that you see in the abundance pattern is directly related to this. Something that is actually kind of dramatic is the substantial lowering cross-sections in the magic numbers. You can see here N50, N82, N126. So what is happening in those neutron closed shells? Well, these nuclei are stable and do not want to capture neutrons, and therefore they have an aversion to capture neutrons. And this is going to become incredibly important. Why? Because the way that you can think about this problem, you can think about it as a flow. So you have a flow of neutrons, and as soon as you reach these magic numbers, you get stagnation of the flow. Basically, the neutrons stagnate there. These nuclei don't want to capture neutrons. So the number of neutrons basically accumulate at that particular location, and therefore you get an anti-correlation between capture cross-section and abundance. It's similar to think about if you're riding in a highway and you have all of these neutrons. There's basically a collision. There's a stagnation of the number of cars at that particular location. The abundance at that particular location increases, and therefore you get a peak there. Yeah. So abundance anti-correlate with neutron capture cross sections, and that immediately gives you an intuition of why those peaks, the first, this is the first, the second, and the third peak arise in the abundance pattern. Now, something that it's incredibly important to realize is, let's sort of focus on the S process. So if I'm capturing neutrons very close to stability, I capture a neutron and I beta decay, and I move very, very close to what we call this beta stability line. So as soon as I get to this magic number, I get a peak here because there's a stagnation of neutrons. I continue my neutron capture, I get a second peak here. I continue my neutron capture and I get a third peak. Okay, so these are the first, second, and third peak of the S process. Now, what happens for the R process? Well, the R process is captured really far away from stability. The time scale has to be relatively short. You get basically stagnation here in the first peak, the stagnation in the second peak, and the stagnation on the third peak. But of course, once the neutron capture ends, you're still unstable and you beta decay. So what you're seeing here is this first peak basically decays, and you see here the projection. So the projection gives me the first peak. The second projection gives me the second peak. The third projection gives me the third peak. And of course, because I'm trading neutrons to protons, the entire peak basically shifts to the left in terms of mass numbers. Yeah. So of course, they had memory that of nuclear structure, but by the time they basically decay back to stability, it seems like that memory is eradicated because that neutron closed shell is no longer, has the right number of neutrons. And however, that gives you an intuition of how this abundance pattern actually takes place. So you can see here clearly the first peak, the second peak, and the third peak of the R process, and they're basically shifted to the left. So a few things to highlight. First is that a single element can be easily produced by both. You can kind of see it here in lead, where you have a contribution to lead for the S process primarily, but the R process still produces a contribution of lead. If you look at, this is my favorite, the third peak is my favorite peak in our process because it has both gold and platinum. And you can see these elements are primarily produced by rapid capture. Barium and strontium are elements that we use to highlight the S process because they're drastically produced by the S process. And europium here, which is in the rare earth peak, is an element whose oscillation strength, atomic oscillation strength, is so deep that it basically produces line features that are very deep in the stellar spectra. And we utilize europium as a way of measuring the R process content. Yeah. The same can be said by barium and strontium, which have very strong lines in the stellar spectra. Okay, so this is basically kind of the nucleosynthesis 101, and at least it gives you some intuition as to what is it that we're trying to achieve here. Okay, so if you step back and say, well, what do we know about R process content in stars? If you like the R process, this should be your favorite star. This is called the Sneeden star, referred to, and is one of the stars that has relatively, the highest R process content. So, its proportion of gold content is significantly higher compared to everything else. I'll talk a little bit more about this particular star. In this plot in the Sneeden review, what you see is basically low metallicity stars, the abundance patterns of low metallicity stars. They have been basically arbitrarily shifted normalization just so that you can see them. But what you can see superimposed there is the R process abundance pattern of the sun. And the thing that it's incredibly amazing there is that the R process of the sun fits the abundance pattern of these low metallicity stars incredibly well. So what does that tell you? That the R process has been operated in an incredibly robust way since the early universe, and that basically, yes, that stars can drastically change in their total R process content, and we'll talk a little bit about that, but that their abundance pattern, that means the element to element ratio, is incredibly robust. That means from a nuclear astrophysics perspective, it means that the ultimate abundance pattern should not depend on the initial conditions that drastically. That means that if you actually change slightly the initial conditions, you should converge to the same abundance pattern. So that's something that is basically come to light in the past decade or so about the robustness of these R process abundance pattern. And what I'm going to highlight here is we're between the second and third peak. So this is usually what is referred to as the heavy R process. And this is where the robustness really arises. Even though we see changes in the first peak, the ratio between the second and third peak and those elements is incredibly robust.
So to interrupt, Enrico, just does this mean then, if you go back to the robustness one, which is so impressive, does this mean that there can't be two different channels? Or does it mean that whatever channels need to choose it, be it, kilonova versus, still the collapsor model, that they have to operate the same way?
Yeah, I think that's a very good question. I think we can talk a little bit more about, the initial conditions there. But you're absolutely right. I think if you invoke more than one mechanism to produce the heavy R process, you better get in both models very similar initial conditions, particularly in terms of the neutron richness of the material. I'll talk a little bit about the rate right now, and that will give you some intuition as to how these core collapse versus neutron star merger process balance with each other. And if you're interested, at the end of my talk, we can talk a little bit about correlations between alpha elements and the R process, and whether or not stellar collapse. What are sort of the constraints on the stellar collapse that need to take place?
Thanks.
But yes, you're absolutely right. I mean, if you have more than one process, you better produce the same abundance pattern. And for the stellar collapse, that's not as simple, at least for the standard stellar collapse abundance pattern, because the neutron richness there seems to vary drastically, and it seems to really have an imprint on the abundance pattern. Okay, so I wanted to show, well, a few things. I mean, the first thing that you notice here, this is, of course, europium over iron abundance as a function of iron abundance. The first thing that you should see is that there's actually a relatively large RMS fluctuations of elements, particularly europium. If you were to compare these with sort of the fluctuations of magnesium over iron, those are 0.3 dex compared to here a factor of 100 or a factor of 500 variations. Another important thing is only a few percent of metal poor stars have clear R process signatures. So only a small fraction of low metallicity stars have R process to the degree in which we can detect it. But I wanted to highlight these two stars. So that's the Sneeden star, which is basically the most highly, relative abundance of our process is the highest that we know. And I'm going to just illustrate two stars that have similar iron metallicity, but very different our process content. And you can see these in the spectrum in a really beautiful way. For example, if you were to look at the calcium lines are very, very similar. But if you look at the europium feature, look at these europium features, incredibly deep compared to one that is almost not there. And you can clearly see here the difference of europium by a factor of 500. And we'll talk a little bit more about where these kind of large scatter arises from star to star. Okay, so if you were to make an inventory of our process material in the Milky Way, a number that you should have in mind is this magic number of 10 to the minus 7 solar masses per year. So that means for a Milky Way-like galaxy, which is forming about 1 solar mass per year, the requirement is that 1 part in 10 million of that is basically produced in our process. So if I take 10 to the minus 7 solar masses per year and multiply by the age of the universe, 10 to the 10, I get about 10 to the 4 solar masses. So if you actually make an inventory of our process in stars in the Milky Way, that's more or less what you get. You get about 10,000 solar masses of basically our process material present in the stars today in the Milky Way. Okay, so as Miriam was alluding to, if you have the standard core collapse supernova in the neutrino-driven wind, we know that core collapse supernova happen once every 100 years. So you have 10 to the minus 2. That means that in order for these events to be viable candidates, they need to produce about 10 to the minus 5 solar masses per event. Yeah, and then 10 to the minus 5 multiplied by 10 to the minus 2 gives you the magical 10 to the minus 7 solar masses per year. Neutron star mergers as an order of magnitude, they happen once every 100,000 years, so about 10 to the minus 5 per year. And so therefore they have to produce about 10 to the minus 2 solar masses per event in order to produce the magic number of 10 to the minus 7, okay? So do we have a very simple argument to make as to, what is the minimum amount of mass required in this event? So I'm going to basically highlight this. So there's something that you can do this actually, it's actually relatively simple, a very simple argument. So if you have a blast wave and these elements are produced energetically in an explosion, you have to ask, well, what is the fastest that I can turn the ejecta and turn it into stars? Well, you have to wait until until you're able to cool that material. And that basically is referred to as the cooling mass. And the cooling mass depends in metallicity to some degree, particularly at high metallicity. At low metallicity is primarily hydrogen and helium that gives you the cooling. And it says, well, I basically expand. It depends, of course, on the energy. And then I said, once I start cooling, if I transform that material into stars, what is the abundance that I get? So in some ways, there's a really nice, simple argument that you can make that tells you what is the minimum amount of mass that you need to produce in an explosion such that you can produce the europium over iron ratios that you see. And the simple argument that you make is, well, the fastest that I can do is basically I take a cooling mass, I put the certain amount of our process, and can I reproduce the amount of europium over hydrogen that I see? And the argument is, very, very simple. You can actually derive the total amount of mass per event just making this simple argument, which gives you a minimum mass estimate. And it's a kind of very elegant way to do this. When you basically then take stars and transform it into this minimum mass energy, what you realize is, for example, this needle star, which is here, requires, a minimum mass per event about 10 to the minus 3 solar masses. Yeah. And the standard core collapse supernova value is somewhere around here. And what you can see is that standard core collapse supernova are actually ruled out as the main contributors to the R process. So ultimately, what you're driven to is that the process producing the R process has to produce a significant amount of mass per event, and it has to be rare, much rarer than core collapse supernova. And this is what Miriam was alluding to. Do I require something like a neutron star merger, which is rare? Or do I take, a very exotic core collapse supernova, 1 in 1,000 or something like that? So that's basically the conclusion. that people have arrived that the production of heavy R process elements need to operate incredibly robustly and at a drastically reduced rate when compared to core collapse supernovae. Yeah, and those are essential characteristics of the R process. And all of these clues are, simply derived from what we see about the abundance pattern of low metallicity stars. Okay, so there's maybe one image that I sort of developed in collaboration with Annalisa there about how to think about this process in a chemical evolution framework. And I won't have time to talk about this, but the way that you should think about this is, if you're enriching the Milky Way with a production, like core collapse, that it's actually relatively common and it produces this tiny little amount of mass, you can sort of make the analogy of a chocolate cookie with a very, very thin layer of chocolate that is very well, spread. Well, if you think about something like neutron star mergers, it's sort of like a chocolate chip cookie in which a significant fraction of the material is actually just highly concentrated. And therefore, in the early Milky Way, what you see is if you have a production avenue that it's rare and produces a lot of material, if you're basically, if stars are turned very close to the chocolate chip cookie, they're going to have a huge amount of R process. And if you're far away from the chocolate chip cookie, you're going to have little R process. And whether or not that's correlated to the large RMS fluctuations that you see in metal content, particularly in the R process in stars. So the idea there is also this rarity also gives rise to the highest RMS fluctuations that you see from star to star. Okay, so how is basically the R process made in neutron star mergers? And here I'm going to focus on a relatively simple channel, which is the tidal ejecta. So I'm going to show you one of the calculations I did in collaboration with Stefan Roswell for my PhD. These are two equal mass neutron stars. The system becomes dynamically unstable. You get mass shredding in the out of Lagrangian points. So a small fraction, about 1% of a solar mass in these tidal tails would be actually ejected above the escape velocity. This is an incredibly robust site for the R process, particularly because all of the neutrinos that are basically produced in the core are not able to shine through these tidal tails. So these are incredibly neutron rich and their composition doesn't change because of the neutrino irradiation. So it's an incredibly robust site for the R process. So I'm going to show you here, just in a second, a movie of how the R process is actually made in real time. So now we go back, hopefully, to this plot that we now have seen, which is basically number of protons versus number of neutrons. I'm going to highlight a few things. So this is the time scale of the simulation. What we're doing is we're showing the thermodynamical and kinematic trajectories of the tidal tails coupled to a nuclear network so that you start seeing the elements that are formed in these tidal tails. You have here in red, this is the temperature of the material, the density in blue, and in black is actually the heating rate. And the heating rate is going to become incredibly important. Okay, but if we think about a t equals 0, a time equals 0, what are the elements that I have? And this is incredibly important, that because of nuclear statistical equilibrium at these high neutron rich conditions, you already have elements that are actually heavy. So you have tons and tons of neutrons, but you also have elements that are ready to actually capture neutrons. Yeah. And what you see here is the abundance pattern at nuclear statistical equilibrium of the element. So that means that you don't actually have to rely, for example, when the material is actually not very highly neutron rich, you have to rely particularly in three-body interactions to actually make heavy nuclei. But here in nuclear statistical equilibrium at these very, very high neutron-rich material, you already have the nuclei, and this is incredibly important. So what you're going to see here is basically how the neutron capture proceeds as a function of time. These are nuclear networks calculated by Jonas Lippener and Luke Roberts, who was my grad student at UC Santa Cruz. So you can see very, very quickly, you capture neutrons, you clearly get stagnated in the first peak, stagnated in the second peak, stagnated in the third peak. And then you basically start decaying back to equilibrium. And what you can see here in the abundance peak is you get the first peak, second peak, and third peak, yeah, as you basically decay back to equilibrium. And a lot of these very, very heavy nuclei that you make are, of course, unstable, and they will ultimately all disappear. Okay, so a few things that are incredibly important to highlight. It's incredibly important to highlight that as this material is basically expanding, both the beta decay and the fission fragments are heating the material, yeah? So as material is basically decaying back to stability, you're actually producing energy generation to the material, and that's ultimately what it's gonna produce the electromagnetic signature. The fact that as you basically expand and you're adiabatically cooling, you're still injecting energy into the material, yeah? And in particular, you can kind of see here that you get significant amount of heating, as you can see, on timescales of a few seconds or so, and then you actually get a power law decay. And we'll talk a little bit about this. And here, this is a standard R process network, which has neutron captures, photo dissociations, alpha and beta decay, and fission reactions. So let me give you just an intuitive feeling of how much gold you produce in one of these events. Relatively, so for example, how much gold we produce in these events is of the order of about a Jupiter mass of gold in the tidal tails. Yeah, so you can make the calculation at $10 per gram how expensive these neutron star mergers are. If this is not impressive enough, you can also say, well, what is the amount of gold stored that amounts to a Jupiter mass, and that's about the amount of gold stored in about 1 million stars. So one of these events actually produce a significant fraction of our process and can actually supply a significant fraction of stars with the R process. And again, this comes again with the rarity of how uncommon these events are, and that's initially related to the fact that we see these very large RMS fluctuations that ultimately, as the mixing increases in the universe, it basically gets eradicated. Okay, so if we were to just give you a little bit of a review of neutron star mergers, as we know, these objects come together by emitting gravitational waves. You radiate both energy and angular momentum. So these objects are assembled. They basically evolve secular by emitting gravitational waves for timescales of gigayears. They become dynamically unstable. Here, I'm just focusing, just for its simplicity, on the tidal tails. Here, the thing that matters is how much mass and the velocity of the material. The velocity of the material is usually related to the escape velocity at the outer Lagrangian points, which depends slightly on the equation of state of nuclear matter and the mass ratio of the two objects. You get basically this instability, you get the ejection, and in a few milliseconds, as you saw, you actually in tens to 100 of milliseconds, you already produce the R process and you start basically decaying back to equilibrium. That decay basically heats the material. So it's basically fighting against the cooling from adiabatic expansion. And once you become transparent, the photons are allowed to escape, and then we see an electromagnetic signature. And that happens, with about 10 to the minus 2 solar mass of material when the material gets to a few AU, so to the size of kind of our solar system. So that implies a peak about few days. So these are sort of the early calculations that took place early on in the field. We just basically realized you can use the same way to describe supernovae. You have basically the expansion of the material, adiabatic cooling that takes internal energy away from you. You get radiation, which is also leaking out. So as material expands, basically, over a diffusion time scale, radiation escapes. And the key is to really understand what the heating rate is. And so these are, one of the earliest calculations from Luke Roberts. And what you see is that you get a power law decay in energy injection. And this is the contribution of a particular element at a given time. So as you can see, there's always at a particular time some element that it's contributing with the heating rate. And therefore, as a result, this was actually predicted by Lee and Paczynski that because you had so many elements decaying that you were likely to get a power law. They were right. You're likely to get you basically get a power law. But what is incredibly important here is that the total bolometric luminosity of the transient is going to follow this heating rate, broadly speaking. Yeah. So that was an incredibly important prediction to be made. I'd like to show this because this is for those of you, I think we all are incredibly interested in the heating rate of our own Earth, particularly because if we want to have a magnetic field, we rely deeply on the heating rate of these radioactive elements. And this is basically the heating rate contribution on Earth. And very, very similar what you saw before. There's a broad range of nuclei that are basically contributing. But in today's Earth, uranium and thorium actually produce a significant fraction of the heating rate, and these are our process elements. Also, potassium seems to contribute significantly. So in today's Earth, these are the elements that are given a significant fraction of the heating rate. This has some interesting implications if you want to talk to me about. But for example, if you have in today's Milky Way 2 stars close to solar metallicity, they can have about a factor of 2 or 3 changes in their R process content, which means that if you make a solar system from that material, you're going to get a factor of 2 or 3 in heating rate. No? So we just recently published a paper saying that maybe the amount of uranium and thorium is incredibly important in producing habitable Earth, because if you have too much heating, you will not produce an alpha omega dynamo, and you would not be able to actually produce a sustained magnetic field. Similarly, if the heating rate is actually too low. So there's some interesting consequences to even life on Earth by the variation of our process. Okay, so if you were to, this is the standard way that we make light curves. If you have a type 1a model, as you know, this is basically given by the decay of nickel to cobalt to iron, and basically the total bolometric luminosity ends up following the heating rate. And in these kilonova models, we were basically expecting the total bolometric luminosity to follow the heating rate of these R process decay. Why are they called kilonova models? Just because they're 1,000 times brighter than a novae. So we would expect them to peak at about 10 to the 41 ergs per second, which is about 1,000 times the kilonova luminosities. Something that it's important is, of course, that the total amount of mass that you have is actually small, and therefore the time for you to become optically thin is much faster, and therefore you peak at shorter time scales, and therefore the luminosity is very low. Okay, something that it's been incredibly important that it's a huge amount of work that took place in advance, and this is work that Jennifer Barnes and Dan Kaysen did, is trying to think a little bit about the opacity of our process material. So you really have a ball of our process material, and the question is how opaque it is as it expands. And what was basically early realized is that the opacity here doesn't depend solely on the number of electrons, but it depends on the complexity, on the electronic complexity, and it depends on the many ways that you can arrange valence electrons in the last energy levels, no? And therefore, it was immediately realized that things like D shell and F shell models, particularly these lanthanide series, which basically have a huge amount of complexity because there's a very large number of ways in which you can arrange these, this valence electrons, can actually produce a significant opacity to the material. And this is actually really beautifully illustrated by this classical paper now by Dan Kaysen, in which you show if you have something like D shell electrons, this is of course iron, this is the type of opacity that you build. The line opacity is a function of wavelength, compared to if you have these lanthanides F shell electrons. In this particular case, you have hundreds of millions of lines compared to hundreds of thousands of lines. So basically the line forest is significantly higher, and therefore you're incredibly opaque all the way into the infrared. Yeah. So it was basically postulated that in this particular instances, if you produce lanthanides, and lanthanides actually lie between the second and third peak. So that means if you have any heavy R process material, then it's going to be incredibly red because the optical depth is going to be so large, the number of lines is going to be incredibly high, the line density, and therefore you're only going to become transparent all the way into the infrared. And that was a prediction made in advance of the observations. Okay, so this is basically how the spectrum looks like. if you have basically very little lanthanides, here 10 to the minus 5, a very small fraction of heavy R process, then the spectrum looks in the optical incredibly bright. There's not significant amount of opacity, but as you increase the number of lanthanides, as you can see, the optical emission basically gets completely opaque because of the line forest that you have, and you only start being basically transparent at infrared wavelengths. So this was sort of the predictions made in advance of the observations, that if you have heavy R process material, it was going to be incredibly, incredibly opaque. And you were not going to be able to actually become transparent in the optical, and all the light energy is actually going to be shifted into the infrared. Another important component was sort of something that Miriam alluded to at the beginning of our conversation before the talk started, about basically can you actually say something about the velocity? Yes. Something that it's incredibly important to realize is that you have so many lines that it's incredibly difficult to basically highlight, oh, this line comes from this particular element, and these spectrum are basically built statistically. You basically know the number of lines, you know the distribution of oscillation strengths, you know the distribution of energy, but in a statistical way, and then you build your spectrum that way, rather than basically, we don't sadly right now know every single oscillation strength and every single energy transition from all these elements. So those spectrum are basically built statistically in terms of thinking about the number of lines. And then what you clearly see is that these line features get stretched drastically by bulk motion. And if you were to do just a cross correlation of the spectra, you can actually derive the velocity of the bulk material. You can clearly see from 0.03 to 0.3 of the speed of light, the lines get drastically spread. And this is very similar to what Miriam sees in 1BC supernovae, in which the line features are incredibly broad. So we had the ability of actually say something about the bulk material. So that brings me to the last part of the talk and telling you a little bit about what were the observational signatures that we infer from this amazing event on August 17, 2017. Here you see the gravitational wave signal. You clearly see the frequency of the signal increasing as a function of time. The two objects are about to become dynamically unstable. Before they become dynamically unstable, we lose sensitivity to this event and we don't actually see the merger. I was incredibly lucky to be part of the 1 meter to hemisphere collaboration. This is collaboration led by Ryan Foley at UC Santa Cruz. We have access to 2 1-meter telescopes. One is Lick Observatory, which is very close to where I am right now. And the other one is the Swope Telescope, which is in the south. So this was our team. We were incredibly lucky to be the first one to detect the electromagnetic signal. As you can see, I'm certainly the oldest person on that photo. We have an incredibly vibrant and diverse team. And I think someone that needs a lot of recognition is really David Coulter here, who actually designed the algorithm of basically say, well, we're competing with these much larger telescopes. Rather than basically going through trying to cover as much field as possible, we're just basically going to go through the galaxies that we know exist in that volume, go galaxy by galaxy. And they did an algorithm in which he sorted the galaxies that were most likely to find the neutron star merger from, and basically did an algorithm that basically maximized our pointing so that we get the largest number of galaxies within that volume. And it's thanks to him that the discovery was made by our team. So this is what we found. Something that is incredibly interesting is that the event was incredibly blue to begin with here, and then it turned incredibly red as a function of time. And this is basically, as we were talking about, the prediction that were made, that if you had second and third heavy R process material, the light from these elements was going to be incredibly red. So as you know, there's lots of incredibly science results that we can talk about: measurement of the speed of gravity, measurement of the Hubble constant, the origin of relativistic outflows and gamma ray burst, constraints on the physics of neutron stars and dense nuclear matter. But I was just going to briefly tell you a little bit about the cosmic creation of heavy elements via the neutral capture process. So the first thing is, really what we have is, does the bolometric luminosity follows the heating rate that we predicted in advance? And the answer is yes. You can kind of see that at late times there's significant discrepancy, and that has to do, as the material is becoming transparent, the fraction of energy that is actually coupled is basically becomes less and less efficient because the material is transparent. So there's a significant amount of correction and arguments as to whether or not this heating rate continues, and how you calculate the bolometric luminosity at late times. But that gives you a minimum mass. You can say, what is the minimum amount of mass that I need in order to produce that luminosity? And the answer is about 0.02 solar masses. Again, these 10 to the minus 2 solar masses that we were talking about, that's more or less what we derive. Now, of course, this is basically assuming 100% efficiency, and the efficiency is not 100%, but at least it gives you sort of the minimum mass requirement. So, the assumed LIGO rate implies about 25 mergers per mega year. Again, very close to that order of magnitude value that I was giving you, 10 to the minus 5 events per year. Or estimates show that an average, total R process mass of about 0.06, when you correct for efficiencies, that's what we produce. And if you multiply the rate by the total mass, you get that the cumulative mass of our process in our own Milky Way is about 10,000 solar masses, which is about the total amount of mass that we see in stars. The total amount of mass that we see in stars is a little bit lower than that, but of course you expect a significant fraction of that to not all turn into stars and still be in the interstellar medium. Okay, another incredibly important thing that we found out is, yes, there's an initial blue component, and there's a significant amount of debate as to where that came from. And it still is actually, in full honesty, is still consistent with a thermal component. So it could have been an initially thermal component. But then, as you can see, this is the two models. This is the models without heavy R process, and this is the model with heavy R process. And as you can see, the spectral models actually produce, a qualitative, match the data in ways that are amazing, providing, given that these models were actually made in advance of the observations. So the conclusion here is that we know for sure, given the opacity of the material, that second and third peak elements were actually produced. No? And if you basically follow the line of argument, we know from stars that the second and third process, the second and third peak is incredibly robust, and therefore, neutron star mergers are a viable mechanism to at least produce the R process today. Of course, this was not at high redshift, this is today, and there's a significant amount of debate as to whether or not these events were actually effective enough at high redshift to actually enrich low metallicity stars. So there's a significant amount of debate, and there's a lot of interesting work that it's been taking place as to what are the sites in these mergers in which you can actually produce the R process. I talked to you about the tidal tail ejecta, which is incredibly neutron rich. We know that in that particular case, we're converging to an abundance pattern distribution that is incredibly robust. Before the two objects, just soon after they touch, there's this argument that they can get this squeeze polar ejecta, heating rate in the interface between the two neutron stars. That material is actually ejected relatively fast, and it's actually thought to produce only the first peak. So there's a significant amount of discussion as to whether this squeeze polar ejecta, which came first, gave rise to the blue component. And then, of course, after the system collapses to a black hole and you have an accretion disk, there's the disk wind ejecta, which we also think actually can produce the R process. And I think today we believe that the total amount of mass that was produced was probably too high for the tidal tail ejecta to actually contribute to the majority of the R process. And people are basically now building models. And this is where we're focusing a lot of our work in really trying to understand the disk wind ejecta and whether or not we can actually produce 0.06 solar masses of material after the object collapsed to a black hole and you're surrounded by an accretion disk. So just to give you a feeling of the sort of models that we build. So here you're going to see the blue ejecta from the squeeze, the initial squeeze ejecta. So this is the blue component. And then, some sort of wind component following after. So you can see, we initially have the squeeze ejecta, which is relatively, doesn't have any second and third peak, is incredibly blue. And then we have the vast majority of mass in the red ejecta, producing a relatively decent feed to the bolometric light curve here and the color light curve. So this is sort of the models that we want to build. As you know, these are one-dimensional models, and the ejecta is certainly three-dimensional. So there's a lot of interesting questions, that still are basically without answer. What caused the electromagnetic emissions? As you know, what produced the jet? What are the properties of the jet? Do neutron star mergers produce heavy elements? It seems yes. Are they source of all heavy R process elements? At least in terms of doing an inventory in total mass, we think that we have the rate and the mass per event. The question of whether this has been operating in the early universe still remains. What was the fate of the merger remnant? Did it collapse to a black hole? It seems like most people believe that it did, and that it was only after it collapsed to a black hole that a relativistic jet was triggered. And of course, what we will see next. And we've been incredibly unlucky to actually not have accurate enough positions in the sky to actually follow other neutron star merger events. But I'll stop there and I'll open the floor for questions. And I thank you for your time.
Thank you very much, Enrico. This is really, really fascinating work. And I'm sure there are going to be lots of questions. So everyone, please use the raise hand feature on Zoom. And while people find that button, I would like to ask the first question, and you were alluding to this a little bit towards the end, which is that, of course, if you assume that neutron star mergers are responsible for most of the R process nucleosynthesis, you could in principle use galactic archaeological estimates with spectroscopy to try and infer something about the R process enrichment rate as a function of cosmic time. And as gravitational wave observatories then come online, you can figure out if these two are consistent. And I envision that that would actually tell you a lot about the process. So is that actually achievable at the moment using archaeological studies? Or are there observational limitations that prohibit you from doing this sort of thing?
Yeah, I mean, I think so we have basically two probes that are very different in origin. Now, of course, we see we can do archaeology at our own Milky Way, and of course, that's the integral as a function of time of everything that has happened in the Milky Way. And then we have the rate kind of calculations from LIGO, which of course, or volumetric rates are actually relatively local, no? Because it's very difficult to detect these events from really far away. So you're absolutely right. As sensitivity gets better and better, we're going to be able to actually see mergers from further and further back in time. The things that I can tell you from the R process in terms of galactic archaeology are the following. One is that people have been looking at dwarf galaxies. Dwarf galaxies have a stellar mass content of the order of about 10 to the 5 solar masses. So from what it's interesting is you say, well, if these events happen 10 to the minus 5 or so per year, integrated over the universe, then you can produce, they're sort of equivalent. It means that in order to get one neutron star merger, you have to produce about 10 to the 5 solar masses of stars. No, so once people are getting to these stellar masses in dwarf galaxies, they look for our process and they don't find. And there's only one galaxy out of 20 so far, Reticulum 2, that has our process. So that also tells you a little bit about the rarity of this process. There's of course people that are trying to do the mass estimate, the total integrate of mass as a function of time, but of course that's plagued by the fact of or completeness in trying to actually find these stars. I think Gaia has built lots of relatively interesting, it's basically shift a little bit the paradigm, because when we're looking at low metallicity stars that are enriched with our process, what people are showing is actually that the kinematics of those stars are basically in counter-rotating or orbits in the Milky Way. So then there's also a significant amount of discussion as to whether those low metallicity stars were actually made in the disk of the Milky Way, or they actually came from from satellites that got disrupted. You're right. I mean, people are looking at correlations between alpha elements and our process. It seems to me, and this is in answer to Miriam's question, that if you want to relate in the early Milky Way with a process that that it's a core collapse process, you cannot produce a lot of iron, for example, or a lot of alpha elements. But for example, a core collapse, a unique core collapse that doesn't produce a huge amount of alpha elements that produce a lot of our process, can be highly consistent with the abundance that we see in low metallicity stars. And finally, a big argument right now is that if you take two neutron stars, the fastest that you can merge them by gravitational waves is about 100 megayears. And the question is 100 megayears too slow in order to enrich, the Milky Way with our process elements when, at low metallicity? So those are sort of the debates. And a lot of that depends on the prescriptions that you use for mixing, the prescriptions that you use of injection, the merger history of the Milky Way, and so forth.
Very clear, thank you. So next question, I think Mariam was next, and you also need to leave quite soon, I believe, Mariam. So please go ahead.
Thanks. So thank you so much. A short question. What do you think are the next steps for the theoretical work that you're involved with? I know kind of the observational work, right? In 2003, we had lots of attempts. Unfortunately, no other kilonova detection despite lots of work. But I'm curious, what are the next steps for the theoretical modeling? You mentioned this, the disk wind, right, interaction, and then also, of course, understanding short GRBs, right? Because this was a short GRB too. So I was curious to hear about your next steps or the field's next steps.
Yeah, I think, we are pretty obsessed with this wind models and trying to do, GRMHD calculations with neutrino transport. It seems to me that getting the neutrino transport right, it's incredibly important because, as you know, these electroweak interactions also change the neutron richness of the material. So getting both the ejection and the composition of that is essential. So this is work that we've been doing and many others have been doing in the field. I think you're absolutely right, thinking a little bit about how the characteristics depends on the mass ratio, how the characteristic depends on whether you have a black hole and a neutron star, and whether or not you're going to see any electromagnetic signatures accompany the gravitational wave. I think where we're spending most of the energy is actually getting the nucleosynthesis right, at the right conditions with the right models. That's, I think you're absolutely right, thinking a little bit about, do you really require a collapse to actually give you a jet? Do you actually leave a magnetar that is stable and that actually produces a significant fraction of the energy? I think thinking now more about the variations that you can get from event to event is something that a lot of people are working on. Theoretically, but I think to me the most exciting thing, I think as we were talking about, is the abundance pattern is just so incredibly robust that our models has to be able to really give rise to that, even when neutrinos are important, and for the disk wind, which seems to be the only viable option to produce that much mass. So I think a lot of the efforts are basically put in that particular area. In terms of of short gamma ray bursts, I mean, something that it's also quite interesting is trying to understand, the sites of, as you've done seminal work on this, where these short gamma ray bursts are basically occurring. Are they consistent with neutron star mergers, with kicks, with distributions? Something that it seems incredibly intriguing to me is that a significant fraction, about a third of all short gamma ray bursts, have no host galaxy to very deep magnitudes. So these neutron star mergers are able to actually leave the host galaxy. Something that will be incredible. I think the simulations that, for example, Annalisa has been doing also in this show that because the neutron star mergers, spread material to much farther distances than anything else, the intergalactic medium should be highly enriched with our process. No, so thinking a little bit about, can you actually detect in absorption, our process material in very low metallicity gas is something that we're also trying to work really hard, but it seems like a very daunting task. So all of the R process signatures that we have come from stars. We have never detected R process in a gas phase.
Thank you. Camilla, please go ahead.
Hi, so thank you for a very interesting talk. I just wanted to make a comment about the chemistry part. So regarding the dwarf galaxies, it's actually now they have seen pure R process stars and pure R process traces based on the barium to europium ratio in a number of galaxies. So it's not an ultrafaint where you can say it's the sole enrichment. So it's not as easy to link maybe to just one neutron star merger. but it's seen in a number of galaxies, also from like really big dwarf galaxies like Sagittarius. So there are definitely imprints in the early stages, also below like -3 or around -3 in various kinds of dwarf galaxies. And what I find quite puzzling and also quite difficult to explain is that if you start looking at Sneeden stars and such stars in various systems, be it our Milky Way, no matter where it comes from, but if you look at them and you look at their overall chemistry and you look at the lighter elements, you also see that they have a lot of carbon. So you must have generated early on and mixed, if it should be a neutron star merger, you must have had a lot of carbon and alphas coming from supernova. I'm not saying, and I don't think that anyone is saying anymore, that it's like the standard common supernova that we believe could do any sort of R process material, but probably rather these rare ones. Now, let's not get into the entire magnetic field and such, but maybe, and I see a need for having several processes. This is also seen at the GCE models from Benoit Coté, where they were trying to just say, okay, if we try to generate all europium in our galaxy at the low metallicity, but also at the higher metallicities, then the delay times do not really add up anymore. So, and also you mentioned the robust part, but if you look at the lighter, the weaker elements such as silver, you also see that they don't correlate perfectly with elements like europium. So to me, there must be additional sources or different tails or parts of the processes. Maybe it's not as robust everywhere, or maybe there's an environment that can generate like a span of elements. So I think it's very interesting to look at. I think also there's a lot to learn still. I just don't think that we can explain all the R process material with just neutron star mergers anymore. And as to the neutron star merger, I also want to just highlight that we found actually strontium, large amounts of strontium in the kilonova 2017 GFO. So we actually have detected in the VLT spectra direct absorption features of strontium and converted that into a mass of about 10 to the -5 or so. So we can actually chemical tag them. So I think there's definitely a lot to learn from the neutron star mergers. I think they are really important for our R process inventory in this galaxy and also in dwarf galaxies, but I think there's still a lot. So I don't know if you have any comments on the weak R process or other sides, Enrico?
Yeah, no, I mean, I agree with you that there's a level of complexity, I think, once we look at the models in detail. I totally agree with you about the carbon enrichment being a big problem. I think my general argument is I really think that if it's related to a core collapse, yes, I'm happy with carbon. I'm certainly not happy with iron, especially in the collapsar model where you're producing 0.5 solar masses of iron. It's incredibly difficult to dilute the iron to europium ratio. So I agree with you that a special core collapse supernova with some interesting nucleosynthesis that doesn't include iron or some of the alpha elements like magnesium, can actually do the work relatively well. I totally agree with you that there's large variations in the first peak, and that the first peak, we also see that the RMS fluctuations of the first peak are less. So clearly the first peak is formed, much more commonly than the second and third peak. So you're absolutely right. There's a mix of processes operating there. I totally agree with you. The issue of the time delay, I think there's a significant amount of debate about, usually those arguments are made because they don't see the europium over iron distribution. And the argument is that both the neutron star merger and the 1A delay are the same. And therefore, if they're the same, you should basically see the correlation in europium of iron. There's now new work that actually shows that the amount of iron produced in type 1A changes with delay time distribution, in the sense that there's more iron produced on supernova that are related to elliptical galaxies versus not. So that's also a significant amount of variance there in trying to understand the 1A. I totally agree with you about the dwarf galaxies being puzzling for neutron star mergers, because we also get kicks, and in fact may be difficult to retain neutron star mergers in those cases. The strontium case, I think I'm a little bit more skeptical about whether or not we have actually found just a specific line feature, just because the calculations that we've been doing, includes hundreds of millions of lines. And when you actually do the calculation, it's hard to find that one particular line at a particular frequency dominates by that much. But I think the work that you've been doing and Derek Watson have done, I think it's incredibly interesting in the sense that the line feature doesn't seem to change as a function of time, that the wavelength actually is incredibly robust, and that you can actually find it in a cross correlation. Whether or not it's just one single line or agglomerates of lines where the oscillation strength distribution and the energy distribution is incredibly narrow, where you have actually a concentration there of lines, I think it remains to be seen. What people are trying to do now desperately is to actually obtain spectra with all the oscillation lines and all the energy scales. But I do agree with you that, yeah, that the field is in its infancy in trying to really understand, the spectral features. And yeah, I agree with you that it seems like if you just take neutron star mergers, they're all the same. They all produce the same R process. They take this amount of time to come into action. The complexity that we see in the observations is not well captured by that single process. So yeah, I agree with you that there's lots of interesting things, and something that Diedrich and I were talking yesterday, which I actually think it's fascinating, is, and you know this well, is of course the variation of our process elements in globular clusters. The fact that you can have two stars in the same globular clusters by a factor of 100 in change of our process. How in the world did you get that enrichment in our process? So that means that, in the gas phase, when the globular cluster was made, there was a factor of 100 in just the gas enrichment within scales of parsecs, which to me, when you think about turbulent diffusion, that seems actually quite surprising. But yeah, I agree that there's lots of puzzles, and I think our understanding it's in its infancy. And I would not claim that the most simple neutron star merger model actually explains all the observations.
Okay, thank you.
Thank you, Enrico. This actually relates to a final thought I had, but I'm not sure if it's a mature enough thought for a question. But in principle, it sounds like it would be possible to, if you do spectroscopy of the ionized ISM in galaxies, and these are sensitive enough, these observations, to detect our process element lines, you should be able to look at how the turbulent diffusion of the local metal enrichment would proceed as a function of different categories of elements, and that might actually, depending on the process generating them, might tell you something. The problem is, of course, you would need a galaxy in which there have been relatively recent events of our process enrichments, and that with such a low rate seems to be very hard to guarantee. But yeah, I don't know if you have an idea of work going in that direction.
Yeah, I mean, I think, and there's also people trying to see if they can detect it in X-ray spectra. Like if there are any X-ray spectral features of these elements, for example, that you can look at it in supernova remnants or in type of environment where you can actually point. I mean, the problem is, of course, that the abundance of these elements is just very small. So just get them to be above the continuum is already a struggle. But if you have a particular line that is relatively fairly isolated from everything in the spectrum, you may be able to see it. There are some interesting observations that you may find intriguing, which is, what people do is they basically drill inside the ocean and they try to look for, uranium content as a function of depth, and then try to derive basically whether or not you see abundance variations. And the current claim, even though the number of, it's a very difficult measurement to make, is that we see uranium variations as a function of depth of the Earth, telling you that some of the material that was actually captured by the solar system, I mean, you have to make them in maybe in dust form or something like that in order to make it through the magnetic field, but that's sedimentation, as the solar system is basically surfing through the galaxy, that you see basically different abundances as a function of depth, telling you that they may be some large RMS fluctuations, or at least sizable fluctuations, even within our own Milky Way. I mean, we got incredibly interested in thinking about what are the fluctuations at solar metallicity, just because of the uranium thorium contribution to the heating rate of Earth-like planets. But I think it's a very hard measurement to make in terms of what are your systematic errors in trying to determine the abundance versus not. But yeah, I think all of these, people are trying to think about can I see ISM local variations of that? there's other people that are saying, well, if I find a cloud that it's 10 to the minus 4 or 10 to the minus 5 in terms of metallicity, and I have a quasar behind it, can I actually see any features of our process enhancement in absorption, for example? This is work that Ryan Cook and Xavier Prochaska here have been trying to do, but they haven't found, appropriate lines that they can actually. So yeah, trying to understand the atomic structure of these elements, as I think as Camilla was saying, I think it's really important.
Yeah, thank you. Let me see if there are further questions. I don't see any hands up. So in that case, first, I would like to thank you again, just for everyone in the audience. I would like to thank Enrico in particular for giving such an incredibly didactic talk at 7 a.m. his local time. I think that is really fantastic. And before we unmute and thank him again with an applause, I have two logistical announcements. One is, of course, Enrico is not here in person now. So if any of you would like to follow up with him in a Zoom chat or whatever, please either send him directly an email or through me, and we'll set that up. And then finally, I'll share a screen briefly to announce next week's colloquium, which is the last colloquium of this winter semester, which will be by Claudia de Ram about physics under the gravitational rainbow, connecting gravitational wave events to a whole different scale in the universe, namely cosmology and large-scale structure and the fundamental nature of gravity. With that, we've reached the end of today's colloquium. So please, if we can all unmute and give Enrico a warm thank you.